Welcome everybody to today's colloquium. It's my pleasure to introduce our speaker for today, Dr. Andre Izidoro. Dr. Izidoro is a candidate for our astromaterials and solar system formation position. Currently, he is sweltering in Houston as a Welch postdoctoral fellow at the Department of Physics and Astronomy and also the Department of Earth, Environmental, and Planetary Sciences. Prior to that, he was the PI of a Young Investigator Grant and Emerging Research Institution at the São Paulo State University of Brazil for 3.5 years. Before that, he enjoyed sunny wine-ridden Bordeaux as a postdoc from 2014 to 2016, studying different aspects of planet formation in both solar system and extrasolar systems. So he knows a lot about them and will tell us today why we're so weird. Prior to being in Bordeaux, he also had a stint in a very nice part of France, in Nice, working with one of the giants in our field, Alessandro Morbidelli, otherwise known as Morbi. Before that, he got his master's and his PhD degrees in physics and dynamical astronomy at the São Paulo State University of Brazil. In his career, Dr. Izidoro has devised multiple innovative solutions to classical models of planet formation, from using orbital resonance to explain inward growth and migration of planetary embryos, to using the asteroid belt's orbital structure to constrain how terrestrial planets are created, to also looking at how planetesimal growth in feeding zones is restricted to within rings. For his scientific and technological contributions to astronomy, he won the Wagner Session Award in 2021. So today he's going to share with us his insights on how the solar system got so weird. Take it away, Andre.
Thank you, Jeff, for this very nice introduction. Yeah, I'm going to talk a little bit about the solar system today and about exoplanets, super Earths, angry gas giants, and let's see if this thing works. Are you able to see my screen? Yeah.
Yeah.
On presentation mode.
It looks good. It's perfect. And we hear you well.
Okay, can you hear me well?
Yep.
Okay, perfect. So first of all, thank you everybody for joining to attend my talk. And before going into the science aspect of my talk, I'm gonna just stress a little bit who I am. So as Jeff just explained, I'm a theoretician of planet formation, and I have modeled several astrophysical and planetary processes of how we build planets, from accretion disks to dust growth, planetesimal formation, pebble accretion, disk-planet interactions, impacts and fragmentation, disk evolution, dynamical evolution of planetary systems, and also the dynamics of stellar clusters and multistellar systems. And I have worked on the accretion of terrestrial planets, asteroid belt, giant planets, and celestial mechanical problems, exoplanets. So what I do is essentially to use constraints from astronomical observation, cosmochemistry, geochemistry, and geophysics to constrain my models. So I use computer simulations and I use these constraints to make sure that my models are corresponding to what we observe. And today, after working on so many aspects, I'm going to put the solar system in the context of exoplanets. So just to outline my talk, so I'm going to first talk about exoplanet demographics, so some stages of planet formation. I'm going to explain my new solar system formation model, talk about hot super Earths and extrasolar giant planets formation, and finally, I will conclude my talk with trying to measure how weird the solar system is. So solar system is clearly structured. So you have these small rocky planets in the inner parts, Mars, Earth, Venus, and Mercury. We have the asteroid belt between Jupiter and Mars. We have these massive giant planets beyond the asteroid belt, and beyond the giant planets, we have the Kuiper belt. So models has to explain the structure to correspond to fairly match the solar system. So if you put the solar system in a diagram, period versus mass, so orbital period essentially measures the size of the orbit, okay? And if you have problems to relate these days, the orbital period in days to distance, I plot them just at the top of the panel. So here you have the Earth, so Venus, Mars, Mercury, giant planets. We can clearly see this structure in terms of masses. If you add the exoplanets that we have observed in the last 30 years, that's what we have. We have here 3 main groups of planets. So the first one is that what's called hot super Earths. Hot super Earths are planets that have sizes or masses between 1 and 20, 30 Earth masses. And they start at very close distance. Most of them are observed inside Mercury's orbit. We can see here Mercury's orbit, semi-major axis is about 0.38 astronomical units. So most of them are closer to their stars than Mercury is to the sun. So we also have these hot Jupiters that are Jupiters that migrate somehow to the very close regions of the disk. And also you have these warm or cold Jupiters. Some people name them using different names. So just to talk a little bit more about super Earths. So super Earths, they are observed in about 30 to 50% of the solar type stars. And one of the iconic systems of super Earths is the Kepler 11 system. So the Kepler 11 system is shown here in comparison with the solar system. We can see that the Kepler 11 has 6 planets, and all of them are inside Venus orbit, as showed by this diagram. So if you look at even closer, you can see that we have 5 planets inside Mercury's orbit. So Kepler 11 is a very compact system of super Earths. So super Earths also come in multi-planet systems, as I show here by the Kepler 11. But we also know that the solar system lacks one here. So if you look at the statistics of giant planets, there is something very interesting appearing in the data. So here again, we have a diagram showing orbital period versus eccentricity. So period gives the size of the orbit, eccentricity gives the shape. So high eccentricity orbit means that the orbit is very elongated in some direction. So I plot here in this cartoon on the right, the orbits of these 4 terrestrial planets and the orbit of a giant planet in a protoplanetary system called HD 2782b. And the eccentricity of this object shown here in red is about 0.95. So we can clearly see that most of the dots between 300 days and 10,000 days orbital period, they have very high eccentricities. These are giant planets. They are more massive than 50 Earth mass overall. And if you look deeper in the statistics, only 10% of the giant planets, like Jupiter, have eccentricities below 0.1. So the square here shows that the solar system planets, as you can see, Jupiter is right here. The eccentricity of Jupiter is just about 0.05 or 5%. So only 10% of the giant planets around other stars have eccentricity as low as that of Jupiter. So just to summarize what I said before, astronomical observations show that most stars have planets. Only 10% of the stars have Jupiters. Out of this 10%, only 10% have Jupiters with low eccentricity orbits as that we have in the solar system. 90% of these giant planets around other stars have very eccentric orbits, like this one that I showed before. And in about 90% of these systems of these stars that we observe, we don't see a Jupiter. But in about 30 to 50% of them, we see super Earths. So we call these systems solar system-like, angry gas giants, angry because they have very eccentric orbits, and the hot super Earth systems. And the goal of my talk is to explain why are they different, why is not the Earth a hot super Earth, and why are not Jupiter and Saturn angry gas giants. So in my talk, I'll describe bifurcation points in planet formation that leads to a diversity of planetary system architectures that we observe. So let's first talk a little bit about stage of planet formation. So planet formation starts in a disk of gas. This disk is mostly made of hydrogen and helium, and one small component, about 1% of the mass, is in the form of dust. Dust is essentially micrometer-sized particles, and they stick together and grow by gentle collisions to what we call pebbles. Pebbles are millimeter to centimeter-sized particles, and then the action starts. Pebbles spiral because of aerodynamic drift in the disk of gas. Why that happens? So imagine that you have the sun and a single pebble orbiting the sun. So the pebble is subject to the gravity of the star and the centrifugal force. Then you can essentially calculate the velocity of the pebble by balancing these two forces. So this leads to the Keplerian velocity. But now if you look at the dynamics of a gas around the star is a little bit different, but not much. So if you have a disk of gas around the star, you have, in addition to the centrifugal force and gravity, the gas is pressure supported because the disk is hotter in the inner disk and colder far out. So basically, the equation, the balance of this force adds this term in the equation. And usually for a traditional disk, this term is negative. That means that the velocity of the gas is sub-Keplerian, is just slightly smaller than the velocity of the pebble. If you put the pebble in the gas, what happens? The pebble is going to feel a headwind. That means drag. And this small difference in the velocity causes the pebble to spiral inwards. And that's very important for planet formation, because in planet formation, pebbles have to spiral inwards and concentrate to make the next step further, right? So pebbles spiral inwards, they concentrate at some specific regions of the disk, and then this region becomes super dense and collapse because of its own gravity, forming what we call planetesimals. Planetesimals are objects with size of 10 to 1,000 kilometers top. And that means that planet formation jumps from millimeter to centimeter size to kilometer scales. So, but for planetesimal formation to take place, you have to have these higher pebble concentrations. That keep this in mind for this talk. So let's now talk about the solar system. How the solar system forms. Something has happened with my slide. It's just open. Okay, now it works. How the solar system forms. So traditional models of solar system formation, they assume that the protoplanetary disk that the sun was born from had a smooth distribution of mass like this in terms of gas and dust. So they assume that you have pebbles, as I explained before, what they are. So these pebbles somehow they grow to planetesimals. Somehow they grow to planetary embryos. So they collide and grow a little bit further. So planetary embryos in that scenario is something like Mars or the moon. But these assumptions leads to several problems and is in conflict with the current understanding of planet formation. So here's a simulation of the classical scenario. So the simulation starts and the gas is dissipated already. Jupiter and Saturn is fully formed in the disk. And you have here this population of planetary embryos and planetesimals that came from the assumptions that we made from the beginning. So I'm gonna just start with some bodies like this, showing this in red and blue. The color does not mean anything here. So I'm gonna play the simulation. The gravity is acting on these bodies. They're gonna interact with each other. The eccentricity increases because of mutual interaction. That means that the orbits are changing. They are crossing orbits, they collide, and they grow to larger objects. If you follow the simulation for a few hundreds of millions of years, what happens is we form a few planets. Sometimes we get 2, sometimes we get 4, sometimes 5. In this particular case, you get 3. So 3 objects. And if you look in particular to this one growing at about 1.5 AU, this object right here, we can see that's even larger than the Earth analog that's growing near 1 AU. So this should be Mars, this should be the Earth, and this should be Venus. Mercury, there's no Mercury in this case. Okay, so let's run many simulations like this and look for trends to see how this model match observations. And here is a plot showing a collection of outcomes as the one I showed before. We plot them together, and you have now distance from the star, again, same measure axis versus mass. So the squares are the real terrestrial planets, and the circles are the simulations. So if you compare these objects that should be our Mars analogs in this case, they are typically 5 to 10 times more massive than the real Mars. And this is what we call the small Mars problem of the classical scenario. So the other problem that you have in this assumption from the classical scenario is that pebbles, they are rapidly lost in the disk because of gas drag. So that means that they might never match the conditions to trigger planetesimal formation. Remember, planetesimal formation requires high pebble concentrations. So the pebbles expires, they are gone, so there's nothing to form planets. How do we get them? So high resolution disk observations by ALMA, this telescope in Chile, shows that protoplanetary disks do not look like this, with smooth distributions of dust. They actually look like this. So the missing ingredient to understand planet formation may come from ALMA observations. So remember, in the case that you have this disk with a smooth distribution of mass, the orbital of objects like the pebbles is Keplerian, the gas is sub-Keplerian, as I show here by these two curves. But in the case that we have those structures, we think something is changing the velocity of the gas. So then these structures are essentially pressure bumps in the disk. At these pressure bumps, the velocity of the gas changes. Why it changes? Because we change the gradient of the pressure. So because of the bump. And that means that this term here might become positive. And that means that the velocity of the gas may be equal to the velocity of the pebble or even higher. If that happens, like at this at the maximum of the bump, what we find is that pebbles are trapped because there's no gas drag anymore. So particles accumulate, and then they may help them to become planetesimals. So if you have pebbles in a disk like this, they drift inwards because of gas drag, but when they reach these specific regions where you have this bump in pressure, they pile up. So if they pile up, you may have the conditions to make planetesimals, and you might make a lot of them. So by how these pressure bumps form them? So there are many ways to make pressure bumps. One potential way is the transition in the disk opacity. So that means how transparent the disk is due to some variation in the pebble size, which might impact the thermodynamics, how efficient the disk irradiates. And then basically, we also can have some sublimation of some specific molecules as water, as they drift and they cross what we call sublimation fronts. So if the disk is colder in the outer part and hotter in the inner part, and there's one specific location in the disk where it starts to condensate water as ice. So that location is the water is no line. And if a pebble beyond the snow line just drift inwards and cross the snow line, what's going to happen is the temperature is going to be increasing. The pebble by just release the gas and sublimates. And another way to make a pressure bump is by some instability in the gas disk. So what we do is to model planet formation, assuming pressure bumps in the disk at specific locations. So this is the major assumption of this work. So we assume pressure bumps near the silicate sublimation line, near the water snow line, and also near the CO snow line of the disk. And then what you want to match with these models, these are the solar system constraints. The first thing that you want to match is the mass of Mars. Mars is the big problem, as I showed in the previous slides. So you want to match Mars, you want to explain the asteroid belt as well. And you can have at least some amount of mass somewhere to make the giant planets and potentially explain the Kuiper belt. So another thing that you wanted to match in this model is the solar system isotopic meteorite dichotomy. So meteorites, they plot in different groups in terms of isotopic composition. So the carbonaceous and the non-carbonaceous materials. So non-carbonaceous material, we think they came from the inner part of the disk, and the carbonaceous one from the outer parts, like beyond the snow line. And by having a disk with no pressure bump, that means that these pebbles might just drift inwards and they get mixed. So if they get mixed, why these two groups of meteorites plot at different locations? So these pressure bumps might help to concentrate confined particles at some specific location, which might explain the dichotomy that we observe in meteorites. But then there's one part of the story that's not completely clear. And this is the composition, the structure of the Kaeper of the asteroid belt. The asteroid belt is this region, hopefully like 1 EU wide, located between the orbits of Mars and Jupiter. And if you look at the specific composition of these asteroids, what we see is that they are different. So the inner part of the asteroid belt, those asteroids closer to Mars, they are typically water poor, and we call them S-type asteroids. So they probably are the main source of these non-carbonaceous meteorites that we observe. And then the C-type asteroids, they are in the older part of the asteroid belt, and they are associated to the carbonaceous meteorites. So that means that we had these two groups of meteorites that have different isotopic compositions, but the asteroids that are a source of these meteorites are mixed together in the same location. So this suggests that these objects, they form at different places and they were mixed later. That's something that you want to match in the model. So final results. So here I'm going to show, again, I showed this plot, this movie in my talk yesterday for the committee, but I'm going to plot it, show it again now. And you're going to have a second chance to make me questions. So we have here dust coagulation simulation. So we are simulating the growth of dust from micrometer-sized particles up to the pebbles, and then pebbles to planetesimals. So then we stop there at this particular case. So the y-axis shows size. So this dashed line, size of what? The dust. Density of the gas, of the pebbles, and of the planetesimals, as I show here by this different color. So these dips that we can see in this blue line are the bumps that we impose in the disk. So and the green is the density of pebbles. I'm going to play the simulation. What's going to happen is the dust that's small starts to grow. When the dust starts to grow, it drifts because the gas drag becomes an important effect, as I can see now. So dust is growing, as we can see. I'm going to play again the next slide. So this dust starts to pile up at this specific location where dust should indeed accumulate. So we can see here that this dust in this location is about 0.1 centimeter in terms of size. They start to drift inwards and pile up at this bump as well. So this pink line that starts to appear in the video is essentially the formation of planetesimals. These are kilometer-sized objects that are born because of gravitational collapse of the dust. So the simulation evolves, and as the disk cools down in time, so these pressure bumps move inwards, and they produce planetesimals from outside in, as we can see. The simulation stops at 3 million years, where we assume essentially that maybe the disk is already dissipating or the Jupiter has formed. And we can see now that we have these three distributions of planetesimals, these pink lines. Just to play the video one single shot again. So this is how it happens. So pebbles start to pile up, produce planetesimals, and the simulation stops. So did you say 3 rings? Yes, 3 rings of planetesimals. And we propose that the inner ring can explain the terrestrial planets, the middle ring can explain the giant planets, and the third ring is consistent with the primordial architecture of the Kuiper belt. So just in this region between the inner ring and the middle ring, there's very little mass, and this is where they're located, the asteroid belt. So there's either very little mass, or in some models, there's no mass at all. I'm going to explain later how we match or how we explain the structure of asteroid belt. So let's now focus on the inner ring. So the inner ring has about 2.5 Earth masses of material. If you add up the mass of the 4 terrestrial planets, we have about 2 Earth masses. So that's enough to make the 4 terrestrial planets. So let's run a simulation following the collisions of planetesimals and planetary embryos in this ring. So, and this is what happens. We assume that Jupiter already fully formed in the simulation. And so, and after almost 150 million years, what we can see that we get 4 terrestrial planets. So some simulations form 4, some simulations form 5, some 3, some 2. You know, the successful rate is not super high, but in some cases we get some good solar systems. Like this one, we have 4 planets and the masses of the planets are fairly okay. Okay, now I'm plotting many simulations as the one I showed before in a diagram, same measure axis versus mass. So again, this color codes dots are the real terrestrial planets masses and some measure axis, and the gray dots are the simulated planets that coming from the model. So we can see now that Mars, so we get a few good Mars in this model. So there's not that dramatic problem of having Mars always 5 to 10 times more massive than the Earth. So even in a few cases, we get some planets that have very little mass as Mercury. Okay, so let's now take a look at what composition this body should be and how they compare. So let's take a look at this Mars first. What we do is to track the collision, the original location of every object that collided with Mars during the history of the simulations in 16 solar system analogs. We got the best solar systems that we produced, that were 16 out of 80 simulations. And then we look at the feeding zones of these planets, where the material is coming from. So what we find is that most of the Mars analogs, most of the mass, so this is a cumulative plot, show where the mass is coming from. Most of the mass comes from beyond 1 AU. For about 30%, 70% of the mass of the Mars analogs comes from beyond 1 AU. If you look at the Earth analogs, most of the mass comes from inside 1 AU. So, and this might provide a way to explain why Earth and Mars, they have different isotopic compositions, because they were formed from material coming from different places. So if this material has initially some different isotopic composition, it should reflect on the composition of the planets. Okay, so now let's see what happens with the asteroid belt. So the asteroid belt is filled by objects that are in the inner ring. So how that happens? They are scattered from the inner terrestrial ring into the asteroid belt. And this is what happens. The simulation I showed before, it starts like this. At the time the simulation starts, we see that we have a bunch of objects, these black objects in this location, and some here as well. So even a few objects in this location. But what happens is most of the objects that are scattered into the asteroid belt come from this region. Why? Just because it's closer. So there is a high probability of implantation of objects from that region than from that region. And at the end of the simulation, that's how the asteroid belt looks like in simulations, if they have enough resolution. Why I'm saying that? Because if you have only a few objects, the implantation efficiency is super low. So, and we want that because the asteroid belt mass is very low. It's only about 10 to -3 Earth masses. So we don't want a lot of mass to end up in the asteroid belt. Otherwise, there's no match. So this preference of implantation of objects from beyond 1.51, near 1.5 AU might explain why most of the asteroids in the asteroid belt that we call the inner part of the asteroid belt that we call S-type asteroid, as I explained, why they and they are associated to the ordinary chondrites, those non-carbonaceous materials, why they have akin isotopic composition to Mars. So it's just because they basically sample the same region. Okay, let's see what happens with the middle ring. So the middle ring produces the giant planets. And that as the giant planets grow, they should scatter planetesimal inwards. In this model, we do not model the giant planets' growth self-consistently using the mass of the ring. What we do is just a simple experiment to illustrate how the process works. So here is a simulation. So we have two bodies initially, this with about 5 Earth masses each, and we are gonna assume that they accrete gas. The gas is this yellowish or brownish region of the disk of the figure. And so we have here this water delivery zone. That means if a planetesimals enter this region, it might deliver water to the terrestrial planet because might cross the orbits of the terrestrial planets that are still growing. So the gray region is the asteroid belt. I'm going to play the simulation, assuming that this modeling the growth of the giant planets, accreting gas from the disk. So the gravity of Jupiter and the Saturn, that they're too small at this point, starts to change the dynamics of these objects that they are nearby, and they're going to be scattered in the dusk. Because of the gas drag, so the orbits tend to be dampened. The eccentricity change to shrink again because the gas drags tend to dump eccentricity. And then they get implanted in the asteroid belt like this. So they are small. Jupiter starts to accrete gas from the disk. The gravity of the system changes, and then we implant a lot of mass in the asteroid belt. And then Saturn essentially starts to grow again. It's scatter another portion of objects in the asteroid belt. So we can also see that's a lot of mass across the orbits of these terrestrial planets. So the region here, we have a lot of objects. I cannot talking in terms of mass. That's not correct, actually. Sorry. But what we can say is that in order to reproduce the asteroid belt architecture, the implantation efficiency cannot be super high. So we can see that's easily to implant, but the amount of mass that we have in this region that probably was small. Otherwise, the implantation efficiency would be too high. But the point is, there is a very wide source region of material that ends up in the asteroid belt. And this explains why you have the C-type asteroids in the belt and why we have water on Earth. So to finally conclude about the structure of the asteroid belt, the inner ring implants the non-carbonaceous material, and the middle ring implants the carbonaceous materials. Okay, so that concludes the story of the solar system. But now let's talk about hot super Earths. So the middle pressure bump sets the destiny of the inner solar system. If there's a pressure bump, 3 pressure bumps, and if the middle pressure bump leaks, pebbles can just go to the next one that's closer to the sun. If it leaks a lot, what happens is, in that previous case, the simulation produced about 2.5 Earth mass of planetesimals in the inner ring. But if the bump is not efficient at the snow line, what happens is this. So we can see that the amount of mass in the middle ring decreases because most of the mass drift inwards and they pile up in the inner bump and they form planetesimals. So the total mass in planetesimals in that case is almost 10 times higher than in the previous simulation. So how that happens? So if the bump forms later, or if the bump is leaky. And this might lead to the production of what we call hot super Earths. So there's the first bifurcation point in planet formation. So imagine that you have these objects growing in the inner ring. If the disk, if the middle pressure bump is not leaking, then what we do is we form terrestrial planets because the mass is small. If the pressure bump leaks, we end up forming super Earths. The direction that we follow, the evolution follow, depends on hydrodynamics of the disk, as viscosity, the gas density, how strong is the bump. And frankly, we do not fully understand this process yet. Another aspect that might happen is the middle pressure bump can also produce super Earths. But in that case, they should be water rich because they accrete a lot of icy pebbles. But then what happens with super Earths? So we can produce super Earths in the inner ring and also in the middle ring. So super Earths migrate. And why is that? So if the planets are very small, like Mars, the amount of migration, that means radial excursion in the disk, is small. It's like the drift. But migration comes from gravity interactions of the planet and the disk. The drift, it comes from collisions of the drag, essentially collisions of the gas molecules with the object. So so if you go to larger masses like the Earth, there is some migration for a typical disk. If you go to super Earth mass, like few Earth mass, then migration starts to be really important. And here's a simulation showing what happens. So in the center of this animation is the star. So this region here, reddish color is the disk of gas. We have a planet that's about 10 Earth masses in the disk, and this planet induces these spiral waves, and they migrate. Typically, migration is inward, but it might also happen outward for this regime of mass. But I don't have enough time to explain that here. But let's take a look at how this looks like in a simulation of planet formation. Again, we have the semi-major axis, the size of the orbit, and the shape of the orbit. This color-coded region show the disk of gas. The planets are interacting with the gas via gravity, and then they're gonna migrate. We have a prescription to model migration in the disk. So they're gonna migrate in this case, following the prescriptions that we have. And some cases they try to migrate outwards, as I said before, and they eventually park at the disk inner edge. Basically, inside the disk inner edge, there's no gas, so there's no torque. So they pile up at this region. And then I don't have enough time to explain what happens really next. But what I can tell you today in this talk is that the migration scenario is broadly consistent with the dynamical architecture of observed hot super-Earths. And we have two papers published in 2017 and 2021, as I showed here, and they became one of the main references in the field to explain how super-Earths form. So, and just out of curiosity, because I know that a lot of people here cares about the Galilean satellites, and I also love them. And I had my PhD student at São Paulo State University, Gustavo Madeira, now is visiting IPGP in Paris. And Gustavo modeled the formation of the Galilean satellites and showed that the Galilean satellite might have formed like hot super-Earths. So maybe the solar system had a mini systems of super-Earths, in fact. So, but what if the innermost super-Earth of the middle ring becomes Jupiter? Then the story changes. And how it changed, I'm going to show in a simulation. So if the innermost hot super-Earth becomes Jupiter, the super-Earths cannot pass because Jupiter opens up a gap in the disk and migrates very, very slowly. And this just blocks the migration of the super-Earths. The super-Earths just pile up behind it and cannot pass. And this basically might be a way to create, for instance, by this is a migration of Jupiter, a hot Jupiter. But that's not really the point of what I want to make here. I want to talk more about the solar system. And the solar system, there's not only one super-Earth becoming a gas giant, but two, because you have also Saturn. So imagine that you have two super-Earths that successfully became gas giant by accreting gas from the disk. Again, we have semi-major axis versus shape of the orbit. And then the super-Earth is going to migrate by type E1 interactions with the disk, that as I showed before. Jupiter and Saturn super-Earths, they migrate. They have this dynamical instability. They collide and they grow. They start with a mass of about 3 to 5 Earth masses, and they grow up to maybe a factor of 2 or 3 in some cases, as we can see. So now we have Jupiter, Saturn, and 3 planets that could be the ice giants. So the masses are good because you have 2 planets with almost the same masses as Uranus and Neptune, but you have an extra planet. So this could be Uranus and Neptune, and this is exoplanet. I'm going to explain at the end of the talk how we get rid of this guy. And maybe this could be planet 9, but I don't have time to talk about it in this talk again. So why we like this model to explain how this ice giants form? Because if you look at the obliquities of Uranus and Neptune, they are tilted. And one potential scenario to explain these obliquities is by invoking giant impacts of large objects, maybe larger than a few Earth masses at least. So these guys, we did look into this in the 2015 paper, and they have, in some cases, obliquities that are qualitatively consistent with the obliquities of Uranus and Neptune. So then we have another bifurcation point in planet formation. So if there is no Jupiter barrier or Jupiter and Saturn barrier, what happens is super-Earths migrate inwards, and we have super-Earths closer to the star. But if you have no Jupiter, then super-Earths are free to migrate all the way to become hot planets. So maybe without Jupiter, the Earth could look like this. And finally, I'm going to talk about the angry gas giants. The angry gas giants appear if you have not only one giant planet or two giant planets or two super Earths becoming a giant planet, but many, as I show in this simulation. So imagine that you have this simulation, this super Earths migrating. One of them starts to become a giant planet as this object here. And then a second one, third one, fourth one. And then they become dynamically unstable because of the gravity is too strong. And then the systems ends up with planets that have orbits that are very elongated. And these are the angry planets that I show at the beginning of the talk with very high eccentricity orbits. Here's a simulation of my former master's student, Evandro Campores, looking at the dynamics of 4 giant planets with about 5 Jupiter masses each in a protoplanetary disk. This is a hydrodynamical simulation. And what happens in this case, confirmed via this more sophisticated approach, is that indeed these planets eventually cross orbits and become dynamically stable. So I'm going to play the simulation, the disk, you can see these nice features of the disk because the planets are interacting with the gas, they migrate inwards, and about 40 million years, there's instability, and I stop the simulation, but the planets are essentially ejected. We can see here clearly that the planets are very close to each other, and they're crossing orbits. And at the end of the simulation, they are ejected. Okay, how do you make sure that this makes sense in terms of observations? We can look at the eccentricity distribution of giant planets, the shape of the orbit. So if we plot an accumulative distribution, so this is shown here in gray, what we can see is that in some simulations, as we show in this 2019 and 2020 paper, is that we can get a good match to the eccentricity distribution of giant planets. Okay, but what happened in the solar system that we did not have instability? Actually, we did, and maybe we are just lucky. So, and this stability is the famous Nisi Model. So, and how I'm talking about that? So I'm talking about that because the ring scenario might be consistent with this view. So the Nisi model requires a very massive disk of planetesimals beyond the orbit of Neptune. And this is essentially our third ring. So the planet is going to interact with this disk via gravity. This is a distribution of planetesimals, just dots, is green dots. So there's interaction. This is our third ring of the model. And they interact. These planets eventually become dynamically unstable, as those simulations I showed before. And this is a way that we get rid of that extra planet in the solar system. Actually, we need that planet to explain some constraints, but I don't have time to explain here. But then at the end, this kind of simulation leads to a successful rate of about 5 to 10%. So again, another bifurcation point in planet formation. If you have fewer giant planets, things don't get very intense. But if you have many, like as I showed in some simulation, what happens is they become angry and they get ejected from the systems, and you leave a planet with a higher centricity orbit. That's a signpost of violence in the system in the past. So the direction that each system follows depends on the disk properties as metallicity, or how much solids you have to make giants. So, and of course, if the system have close encounters, that mean orbital crossing during the stabilities or not. Okay, so that closes the story of the angry gas giants. Now, the solar system. How unusual, weird, rare is the solar system if you use the current data to measure that? If you could observe the solar system, that's what we would see. Not much. So because it's really hard to observe objects that are very close to the star, and it's really hard to observe objects that are very far as well. Objects that are small, very close to the star, and objects that are large but very far. So the only planet that we would be able to detect with lucky, if you're observing the sun, would be Jupiter. And then we will be able to measure the mass at some level, the size of the orbit, the shape of the orbit, and that's it. And then, if you look at what happens with these stars nearby the sun, if you're looking at this of 30 light years, what we see is that most of the stars are not like the sun. The sun is a G-type star, and most of the stars that we observe are low mass stars, M-type stars, like that star that TRAPPIST-1 orbits. And then, so sun-like stars, they are about 10% of the stars in the solar neighborhood. So let's make some calculations. We know that 10% of the stars in the neighborhood, solar neighborhood, are like the sun. So there is no super Earth in about 50% of the systems, as I showed in one of my first slides. Only 10% of the systems that we observe today have giant planets. Out of this 10%, most of them has very eccentric orbits, 90%. Only 10% have low eccentricity orbits as Jupiter and Saturn. Then we can do a simple calculation to understand how unusual the solar system is. So 10% of the stars are like the sun, 50% of the system has no super Earths, 10% of the system have Jupiters, only 10% have Jupiters with low eccentricity. So that gives 0.05%. That's about 1 in 2,000 with the current data. So now let's do a philosophical exercise. Using the current data, I want to make sure that the sample is biased. So this is just an exercise. We have about 500 billion stars in the galaxy. If you multiply this by 0.05%, we get 250 million solar systems. Okay, there's no error bars here, so I don't know them. But let's just make another calculation. Let's assume that you are wrong by a factor of 1,000. Then we still have 250,000. If you are wrong if you're just underestimating the fraction of solar systems, that would be scary. And just to conclude the caveats and conclusion of my talk, so we need to confirm these pressure bumps via observations and theory. We have to observe young disks and make sure that these pressure bumps are there. So we have to understand the correlation between planets and slow lines and the structures of ALMA. So it's important also to understand the Jupiter role on keeping the dichotomy. And then I have a lot of questions to answer, to address in my model. Is a single generation of planetesimals enough to explain chondrites? Giant planet formation in the middle ring. So you have to model it in a self-consistent way. So it's also important to keep in mind that other solar system formation models exist. We have the Grand Stack, and we have the early stability model, and you have to now to distinguish them. So how we constrain super Earth's formation? So you have to understand a little bit more about their composition, if they are rocky or if they're icy. So, but I think we are going the right direction, but many open questions remain. And I stop here and I take questions.
Thank you so much, Andre. That was a great talk. It's nice to see how we are weird, but in a good way. Many points in your talk, I kept thinking, we don't talk about Bruno, because you get to a point where you're like, yep, I can't talk about that. That would be another talk. All right, do we have questions for Andre? I see Manel has one in the chat. I'll read it out for you. Won't there be a bias in radial velocity surveys towards detecting high eccentricity planets, just like transit surveys are biased towards close orbits? Yeah, we have bias, even for closer in planets, and for some level they are affected. And that's why I try to make the point that using the current data, and there is some big error bars in all of this, in terms of at least the final of the talk. Yeah, but one of the things that seems to be emerging the data, for instance, is so like in terms of Jupiters. So it seems that the occurrence of Jupiters is decreasing after 10 AU. So you tend to see fewer Jupiters after 10 AU. So that's a kind of trendy that's emerging the data, but we have to understand a little more about that. All right, thanks. I see Katerina has a question.
Yeah, good afternoon. Thank you for your talk. I have a question about one of the slides where you showed the traffic jam and for the Pebble model, where you showed the various condensation fronts. If condensation fronts are acquired to build up the mass density, and if you are required to have this pressure build up in the nebula for planet formation, are you then not limited by the number of condensation fronts that you have? I think you showed 3, the CO, the water, and the silicate. That gives you 3 fronts, and in a naive and very simple-minded view, you would say, okay, then I get 3 planets. So if that were the case, how you make 8 planets for the solar system, or other planet or multiple planets in various systems, how do you get around that?
Yeah, actually, each one of these pressure bumps, they may induce the formation of these rings, and each ring can produce multiple planets. So you can have, like, in the inner ring, we produce 4. We can have multiple planets forming in the middle ring. So, and as soon as you form, like, imagine that you form a core, so like a Jupiter's core. After Jupiter's core formation, this core induces the formation of another bump, and then things become very complicated. But yeah, in each pressure bump, we can make many planets.
So then what is the key physics determining how many planets you can form within a ring?
I don't know. We don't know yet. Nobody knows. Yeah, we don't know. Maybe just the amount of mass in the disk, but yeah, we have to understand that. Yeah, this is why we form, for example, Jupiter, the solar system. Why we got, like, maybe my models, they tend to favor the formation of 10 cores, like Jupiter, Saturn, plus 5 to 10 super Earths beyond Saturn. But why the model favors this number, and how we can explain this number, we don't know yet.
Well, I'm surprised about that, because I thought the physics must be underlying in the model. So
yeah, what happens is when you are growing from planetesimals by collisions, we end up growing some oligarchs, and the number depends on where you are in the disk. If you're closer in or far out, and then which process is on action. If you have available pebbles, if you have available only planetesimals, and then might change. For instance, in some of these models, the middle ring, it might have, at the end of, like, after 3 million years, it might have a lot of mass in pebbles, like almost like 50 Earth masses left, and that's still could continue making planetesimals. Or in some disks there is 0. Depends a lot of for example the initial dust to gas ratio of the disk. So the model is extremely sensible, and yes.
Does the model also change as those pressure fronts change? And if it sticks in one spot for any point of time, you can start to form a planet, then it might, move, and it might not move smoothly.
It's complicated.
So that would suggest in any one ring, you're forming planets at different times, or are you actually within a ring?
Yeah, that's that might be a way to explain. Like, if you look at the middle ring in particular, so you can see that near 10. Can you see my screen?
No, I can't.
Oh, sorry.
It stopped sharing.
Sorry. Okay. And now?
Yep, looks good.
Okay. So if you so this direct lines. So this is where the planetesimal starts to form, and then as move inward, these are the late formed ones. So yeah, there's this planetesimal production fronts that move inwards. This form early, like near 0.1 million years, and this one form near like 3 million years. So yeah, there's this difference in time of formation as well.
How about Ryan next?
Thank you, Andre. Can you gave a little slide there about the Galilean satellites. You mentioned that they form like hot super Earths, but at least the outer 3 have a lot of ice in them. So how does that? Yeah, it was a few slides up. So you
Yeah,
can
that's
teaser of that.
that's one of the results that we have. It's actually consistent with that. So we try really hard to explain how we could avoid them to get a lot of ice. And in our simulations, the 4 satellites, they have a lot of water. So the innermost ones, they typically has a little less, like typically like 20% water mass fraction. But the 2 othermost ones, they are just like 50%, because in the case of the Jupiter, the circumplanetary disk, has a different structure in terms of temperature, and the snow line is quite close to Jupiter. So the planets mostly grow, the satellites in that case mostly grow beyond the snow line. That's why they are water rich, and they migrate inwards to near Jupiter. Yep.
So you said Io has 20% water?
Yeah, and yep. Then at the end of the model, when we modeled that, we did not understood that, and we tried to explore other options in the model to try to conciliate the pebble accretion view with the Galilean satellites. But at the same time, we are working on that. There was a paper by Francis Nemo and I think grad student, where they show that during the accretion of Io, and so you might just dehydrate the planet by hydrodynamical escape. And then, yeah, we propose that that could be a potential solution for the issue that we see in the model.
Great, thank you. I think Bill has a question.
Sure.
Yeah, hi, thanks again. I want to talk about the isotopic dichotomy. I'll make a comment. So in this model, you've got the 3 rings, and presumably they're all forming simultaneously. So you're going to, let's say if you have a gradient of the slight variation of R process versus S process, nucleosynthetic isotopes, then you can explain the dichotomy you showed, but it would predict, I think, that if we could get a really macroscopic comet sample, something from the 3rd ring, it would be a 3rd group. I think that would be very interesting.
Yeah, I agree. Yeah, I fully agree with you. That would be nice to see, or
But the one thing we already have, of course, are tiny bits of stardust from the stardust samples from the comet, and some of those things are chondrule fragments. So there's stuff that's coming from closer in and is being sent out. So in this model, all of the pebbles drift in. I don't see how anything being transferred back out.
Yeah, this transfer should start a little bit earlier than the simulation starts, when the disk is still building up. Yeah, we do not really model that in that particular case to make things just simple. Yeah, but yeah, during the disk build up, when the disk is still spreading, then we should have this transport of materials. Yep. And
the 3rd ring also predicts, since everything is forming coevally, that you're going to have early formed planetesimals far out, so they're going to melt from aluminum-26 heating and even make iron cores. So there should be differentiated comets out there.
But then there's a question of what is the amount of aluminum-26 in the other solar system versus the inner solar system? Are they the same?
Yeah, Andre, we've measured aluminum-26 in a few cometary rocks, and there's so far none.
Okay.
You see, no difference or none?
None. Aluminum-26 to 27 consistent with 0.
That's I haven't seen that. Have you published this, Ryan?
Yeah. And so, Andre, like, how are you supposing this non-homogeneous disk originated in the first place? Like, we assume this our molecular cloud was well mixed, right? I always wondered about this. So how did these gaps really preserve a dichotomy or a trichotomy that was there in the first place? And they didn't create the dichotomy, right? So where does that come from?
No, if you, I don't know how you could do some thermal processing in the disk. with this model. So we assume that the dichotomy is already there, and then we start. That's an assumption of the model. Yeah. So I don't know how to build the dichotomy in a different way.
I'm just going to pipe up Ryan saying that if there was a gradient in aluminum 26, that could mean that the second ring would have, let's say, a little less, and things would happen more slowly. So the timing that Corot et al. Advocated for planetesimal melting and accretion out there could actually be the same time scale as in the inner ring. Just there's just less, because it's all tied to aluminum 26.
Yeah.
Heating.
Yep. Yep. Yeah. Cool.
All right, we have one more
Very
question
interesting.
in the chat I wanted to get to because it was one that was on my mind. Great talk from Zoltan. Can your model accommodate a late, roughly 150 million year moon forming impact between a proto-Earth and a planetary embryo?
Yeah, I did not check the numbers yet, but given my experience with like the classical scenario, yes, we should see a spread on the timing of the last giant impact, and I would guess it should be between 20 to 250 million years. So you should have some collisions happening just at the right time between, like, let's say 50 and 150. Yeah, but I know I still have to look into this, how many are happening at the correct time. But I don't expect the result to be very different from the previous simulations of the classical model. And another thing that you want to track as well in this is the isotopic composition by looking at the filling zones of this of TIA, to see if it's consistent with the isotopic composition of the Earth. Yep.
Thanks, Andre. Any other last questions before we let Andre go for the day? All right, well, I want to thank you one last time. It was a fascinating talk and looking at different ways for explaining the exoplanet systems that we see and breaking some of the old molds. All right, have a great day. Thank you.
Thank you.